All right, so in the curvilinear aspect of velocities and accelerations, it can get pretty complicated. Before, we only cared about a particle moving in, say, a straight line or in a Cartesian coordinate where the acceleration was only changed, say, by rectilinear force, or say we had a box and the force was the only means of changing the acceleration. Okay, but in a curvilinear system, you actually will have to sometimes change coordinate systems because it's easy to track the movement of the particle. When you have a curvature, you can change the velocity, but you can also get an acceleration term because of the change of the direction. So remember, since the acceleration is a vector, I, j, k in rectilinear in Cartesian coordinates, you can change the acceleration by changing the magnitude or also by changing the direction. Okay. In that case, when we move to a different type of coordinate systems, you can change the radius of the path, for example, of the arc, or you can change the magnitude of the arc. So it's gonna get a little complicated in terms of the amount of computations that you have to do. But it's very interesting because that's offers a very elegant way of capturing the acceleration and velocity and displacement of particles moving in curves and in paths that have arcs and in using different coordinate systems too. So in general, curvilinear motion is given when a particle moving along a curved path undergoes a curvilinear motion. Okay, so we're going to start defining this curvilinear motion. Since the motion is often in 3 dimensions, right? Sometimes we analyze just 2 dimensions, neglect one, or assume that it's only moving in 2 dimensions. But in real life, in real world, you have 3 dimensions to worry about. And in that case, vectors are used to describe the motion in 3 dimensions. So many times I've written R3 because there are 3 dimensions, and also a 4th dimension could be time. So let's consider a particle that moves along a curve defined by the function s. So there's a path and is described by a parametric function s. And if you want, pause this lecture and look into parametric functions. It's not something that we're going to discuss here, but this is very useful to characterize the path of curvilinear motion. So just for now, consider a path function s, and and the particle p is going along that path. So we can describe the position in terms of a distance from the origin, and that distance could vary or could be constant, call it r. And then actually you can also track the new distance with an angle. So there are different ways to track the distance. That's the beauty of having different tools and different coordinate systems. So the position of the particle at any instant is given by r, obviously, right? The position of the distance. But r is a function of time because at this instant, this position is in this r, and an instant later, it could be this r further away. So if this radius is constant, and remember, this is just not radius, it's just not a constant, this is a vector, because it's in 3 dimensions. So that's why it's important to have this, because if we have a cylindrical coordinate where the r moves along z, then yeah, maybe the r is constant. But if we choose a point here, then the r's are not constant. So that really depends on what coordinate system you choose. That's why in kinematics, we care about the change, or better, the geometrical aspects of motion. Okay, that's part of why we're studying this. versus kinetics, we care about the forces that are making that motion happen. Okay, so r is a function of time. So we'll have to find the r dt when we want to find the instantaneous velocity. So let's talk about velocity. The velocity represents the rate of change in a position of a particle. We know this. The average velocity is the change, the delta in r divided by the delta t, versus the instantaneous velocity is the time derivative of the position, is the velocity at each instant. So in average velocity, this particle moved this much, delta r, and it took certain delta t, and that's the average velocity. But instantaneous velocity, we know exactly the time and the moment and the distance. The velocity vector is always tangent to the path of motion. Okay, so the velocity vector, as this is given, this is the velocity vector. It's tangent to the path of motion. So this is a question that you should be able to answer in your quiz. The magnitude of v is called speed. So velocity has a magnitude and direction. You can have a negative velocity if you're moving on a negative side of your coordinate system, or a positive velocity. The magnitude is the speed. Okay? Now, the speed can be obtained by differentiating along the path. So remember, if we have a path, then we do the derivative of that path, which is a function in terms of s, and we get the speed, which is not a vector. Similarly, acceleration represents the change in velocity of a particle. And again, we can have average acceleration just by a change in velocity between 2 points, 2 instants, and the time they took, all right, delta v. Or we can have the instantaneous acceleration, which is the second derivative of our distance, r.